Well, good afternoon. This is 2:31 on Monday, the 28th of September, 2020. It's, like I said, 2:31. Here comes the student. Can't see who it is now. As soon as it fades away, I'll admit him. It's Kara coming in. So let me get Kara present. Okay. All right. Good to see you, Kara. I don't see you yet, but I see you. Oops, I think somebody else is coming in. Unfortunately, Zoom or somebody is blacking out my screen, so I can't see who it is coming in. I can't check to let you in. Miguel or Jesus is here. So we got the top of the alphabet, the bottom of the alphabet. It's those in the middle, not here yet. Okay. So let's go to make sure. Yep, I only got two people here, so I'm going to minimize this. And I'm also going to, I don't know why I've lost Kira, but she's here. I've lost myself. I'm here too. Anyway, any questions, issues, concerns, problems, anything you want to bring up? Either one of you? First, let me make sure you can hear me. Can either one of you hear me? Okay, good. I wanted to make sure the sound was on. I've had some times when the sound just wasn't working, so I just wanted to make sure I wasn't talking to the wind here. Okay. All right. So no questions, issues, concerns? All right. Well, what I think I'm going to do while I've got this screen up, I'm going to move Miguel up to the top, or Jesus up to the top. Okay. Now, if there's no questions, we'll just pick up where we left off last week. We were talking about linear equations, and just as a little bit of review, let's see if page up, that doesn't work. Let's see if arrow key, that doesn't work. Okay, see if this works. Okay, just as a reminder, what do we mean by a linear equation? Okay, here is one representation of a linear equation. dy dx is equal to p of xy plus p of xy is equal to f of x. Now this is the one where you have the coefficient function of 1. Those are fairly easy. The more general view, I mean not easy, but easy to deal with. The more general view of a linear equation would be something like this. Didn't realize I was going to have to go this far back. So there, well, no. Okay. We'll get to it in a minute. Okay, yuck. Just on back here. All right, that's our standard form where the coefficient is 1. But more generally, our function looks like this. This is the most generic form of a linear first order differential equation. A of x dy dx plus a0 of x, a1 of x dy dx plus a0 of x times y is equal to some g of x. That first order differential equation is said to be a linear equation in the variable y. Now, notice what the first thing they said: by dividing both sides of the equation by the lead coefficient a1 of x, you find a more useful or standard form. This is where we always start. Not with this one. Well, I mean, we may start with this, but we always get it to this form first, because this is what we're built on. But notice what we did. We divided by this a1 of x. Now, what we're about to hit now is, what if this a1 of x is 0 anywhere in the interval that you're interested? That could create a problem. Okay? So let's go back to where we were, and that's where we're going to pick up today. So let me scroll down. This is pages away now, so hold on. Pages away. Okay, we're getting close. All right. Oh, wait, here's someone trying to come in, and unfortunately Zoom or somebody blacks out their name, so I can't let them in. It's Ryan. So let's see, should we let him in? I don't know. Let's let Ryan in. Okay, so the top part of the alphabet is moved into the lead here, 2-1 against the bottom. So hopefully more will come in and help Jesus hold up the bottom of the alphabet. Okay, he's having to do it all by himself right now. Okay, so Ryan's here. So let me clear this out of the way and go back here. Now, Ryan, we were just talking about, first, any questions, issues, problems, concerns before we proceed? I just took them back and reminded them what the general form of a linear differential equation, first order linear differential equation looks like, and then what our standard form looks like. Standard form has a coefficient of 1 for the dy dx. The general case has some other function there. Okay, so except in the case where the lead coefficient is 1, that's the standard form, the recasting of equation 1 into equation 2, that's from the general form to the standard form, requires division by a1 of x, and that's what I just took you back to show you. The values of x for which a1 of x is equal to 0 are then called singular points of the equation, because you have to get there in order to solve it the way we've been doing it, but by doing that you're introducing these singular points. These singular points are potentially troublesome, you believe that, and specifically in equation 2, if p of x formed by dividing a0 of x by a1 of x, you'll have to go back and look at the earlier pages here, is discontinuous at a point, the discontinuity may carry over into your solutions of the differential equation. Now, they have a side note here. I don't know if this is worth reviewing. In case you're wondering why the interval 0 to infinity is important in example 3, which is what we did last time, read the paragraph and the paragraph following in example 4. So we'll come back and do that. I think we already talked about it, but if not, we'll do. So let's do example 4. Okay? What we're doing is trying to find a general solution for this differential equation. Okay? Now, I think I'll go to the whiteboard and we'll work it out there. Okay, find my pen. Now somebody else trying to get in the class. I don't see that they are, but I need to do a little bit of maneuvering here. So I'm going to move this as far up and to the right as possible. Is there a question? Say that again. Are you talking to me or someone else?
Oh my gosh, I thought I was, excuse me in my foul language, I'll be putting myself on mute.
Okay, you cut yourself off, which is probably not a bad idea. Okay, all right. Let's do equation 4 if we can set that up to do. Here's my pad and here's my stylus, or whatever you want to call it. It says find the general solution of this. X squared minus 9 dy dx plus x y is equal to 0. All right. Now, in some senses, it's a pretty straightforward problem. Okay. This is not one, I don't believe, that you can solve by separation of variables. So hang that up. Don't believe it's going to work. Okay. This is in the general case. We need to get it into our standard form, which involves dividing by x squared minus 9. So we'll divide each term by x squared minus 9. Dividing this by x squared minus 9. And dividing 0 by x squared minus 9, which is sort of meaningless because anything divided into 0 except 0 itself is 0. Okay, so that's going to go away. Here we got rid of our coefficient function here. That's what the plan was. But at the same time, I would say going out here and say x cannot equal plus or minus 3. Why? Because we just divided by this thing, and if x were equal plus or minus 3, that meant we just divided by 0, which we can't do. So these are potentially singular points for us. We don't know that they will be, but they are certainly potentially singular points for us. So let's rewrite our equation. dy dx plus x over x squared minus 9 times y is equal to 0. Okay, not an initial value problem, so we don't have anything there. Now, what's the first thing we do? Once we get it in standard form, that was the first thing we did, we find our p of x. And p of x is the coefficient function of y when we have it in standard form, when we have this in as a coefficient of 1. And what are we going to do with it? We're going to integrate the p of x. So the integral of that p of x, which would be x over x squared minus 9 dx. That's what we're going to do. That's your integrating p of x. Well, this calls for, anyone remember which technique we use for solving an integral such as that? There's a real tendency to say partial fractions. But on the other hand, I think a simple substitution would work. Let's try it. Let, of course, the most complicated part is your denominator, u equal x squared minus 9. Then du is equal to what? Y'all are really in there today. Must have been a fun weekend. Okay, 2x dx. Well, we have an x dx. We need to get rid of the 2, so we're going to divide both sides by 2. Okay, so that leads us to 1/2 the integral of du over u, which is 1/2 the log absolute value u. Now don't do a plus c with this. This is the integral of p of x dx. Go and leave it like that. Okay? Now that's a fairly convenient form to do, because what we're going to do is change that by a basic rule of logarithms. This will be log of u to the 1/2 power. Absolute value of u to the 1/2 power. The reason for that, the next thing we're going to do is this. Use that as a exponent for your exponential function. The reason I moved the 1/2 up there is that e of log is just absolute value of u to the 1/2, which when we go back and put in what u is, that's absolute value of x squared minus 9 x squared plus minus 9 to the 1/2. You know what I'm going to do? I'm just going to go on and put this under a radical. Okay, I'll probably regret that later. That way I don't have to write the absolute value bars, because obviously what's under there can't be negative. Okay, so what that tells us is that x has to be between minus 3, no, I'm sorry, basically greater than 3. Or it could be less than negative 3, couldn't it? Yeah. So either let's see, I don't know how best to write this. Less than negative 3 or greater than positive 3. One or the other, okay? Because that, two reasons. One, it can't be plus or minus 3 from up here, and it can't be between negative 3 and 3, because then that would give your radical a negative number, and we can't have that. Okay, so we've really got some restrictions on x here. All right, but let's proceed with our thing. This e to the u, which is this thing here, I'm going to rewrite this as the square root of x squared minus 9. This is our integrating factor. So let's take it and multiply it by everything. That would give you the square root of x squared minus 9 dy dx plus. Now if you multiply the square root of x squared plus minus 9 times 1 over that, you wind up with x over the square root of x squared minus 9. Okay, that's a pretty ugly 9. Y is equal to 0. Okay, hold on just a moment. All three of you were in. No, Ryan wasn't. Ryan, I just got back from a long weekend at the farm, and I'm incredibly tired. Had a late night last night, very early morning this morning. Had to be up by 4:45 Eastern time, which is 4:45 our time. I've been at it since then, so it's pretty much hanging on by a thread here. Hold on just a minute. I am worn out. I'm trying to keep enough caffeine and sugar in the system to keep going. Okay, so that's our differential equation now. Now, what we want this to be, and supposedly by multiplying by our integrating factor like we did, we should have made this a perfect derivative of the integrating factor, the square root of x squared minus 9, my pen is not writing well, times y. Now let's see if we made the left-hand side that. Okay? Let's take a derivative. This is a product. If I could get the pen to show up. There you are. A product, so it's the first, there it is, times the root of the second, there that is. Plus the second, y, times the root of the first. Now I want to write that as back as this, x squared minus 9 to the 1/2. Take the root of that, you have 1/2 x squared minus 9 to the minus 1/2. Power rule. times the 2x. Okay, the 2 and 2 will cancel out, and you have x over x squared minus 9. That's exactly what we've got, times y. So we do have that, and that's equal to 0. We'll write that in differential form and put your dx over here, and that gives us the square root of x squared minus 9 times y is equal to, and if you integrate this, that's a constant, okay? And that means that y is equal to that constant over the square root of x squared minus 9. Now all our conditions are still applying, okay? X can't be plus or minus 3. That would give you a 0 in the denominator. And x either has to be less than minus 3 or greater than positive 3, because that otherwise you have a negative under a radical. Can't have either one of those, so that's where we're stuck. Okay? Now, that would be our solution, and that's exactly what they get here, but understanding you have singular points at x equal plus or minus 3. Now, depending on your initial condition, if you're, whoa, here, well, evidently Jemanuel had to leave and come back because he was already here. No, he wasn't. Okay, sorry about that. That was the last class he was here. So now the bottom half of the alphabet is caught up with the top half, 2 and 2. If James makes it in, then we're split right down the middle, but who cares, because we're a perfect attendance. So let's make sure James isn't waiting out there somewhere. Nope, 4 participants, and that's what I've got, because I don't count. Okay. Okay, I'm going to scoot Ryan up just a little. Okay. Now, there's our solution. But remember, x can't be, we have singular points at x equal plus 3 and x equal minus 3. So if either of those have meaning to the problem, what we did just wiped out that meaning. Okay? So let's go back to the book. And see what they say. So here's how we worked our problem, which is pretty much like we did. We divided both sides by x squared minus 9, gave us that. Now, it says here, although p is continuous on negative infinity to negative 3, and they say, and it would be, p would be continuous on minus 3 to 3 and 3 to positive infinity. In other words, the only two places it's not continuous is at minus 3 and plus 3. Minus 3 and plus 3. Okay? We shall solve the differential equation in the first and third intervals. Okay? This one and that one. Why? As you'll see, this one comes up with the square root of a negative number. We can't do that. Okay? So in those intervals, you take the p here, x over x squared minus 9, integrate that, and that gives you exactly what we got. Integrating constant would be the square root of x squared minus 9. So that's where you see you have to leave off the interval from negative 3 to 3. Hold on just a second. Sorry. This weekend, I think I got dehydrated, and I still haven't caught up yet. And then traveling, I try not to drink much anyway, so got even more dehydrated. So sorry, I'm having to rehydrate here. Now, when you multiply your standard form up here by the integrating factor here that we got from e to the integral of x over x squared dx, and they did it a rather bizarre way, but it still worked okay. You get the square root of x squared minus 9 times y is equal to c, and then this final form, which is exactly what we got. So we may have gone about it differently. We got the same result. And you're stuck with negative infinity to negative 3 or positive infinity to, positive 3 to positive infinity. Can't use the ones in between or those values. Can't use those values because you divided by that, and you can't do the things in between because you took a square root of that. And so you have to be outside of those. Now, here's what I was trying to get at before, and that was just review for what we did, showing they came up with the same answer. Now, notice in example 4, x equals 3 or minus 3 are singular points in the equation, and that every function in the general solution is discontinuous at those points. On the other hand, x equals 0 is a singular point of the differential equation in example 3. Now that's a previous one, but the general, excuse me, I'm so sorry. Again, I'm running out of steam. And I just drank the last of my artificial steam, so I hope I can make it from that point on. We'll see. It says, and back in example 3, which we did last time, we see x equals 0 is a singular point of the differential equation, but the general solution is noteworthy. This is of the previous one, in that every function in this one parameter family, c is the parameter, is continuous at x equals 0 and is defined on the interval from minus infinity to infinity, not just 0 to infinity, as stated in the solution. However, the family is defined on that cannot be considered a general solution to the differential equation, since that singular point still causes a problem, and that's what they're going to refer to problems 50 and 51. So it's a lot of blah blah blah. Basically what you have to watch for, anything you're doing, if you create a singularity, you have to account for it. You can't just wait till the end and say, oh, it took care of itself. No, it didn't. You can't divide by 0, no matter if it doesn't show up being a problem. So let's do example 5, an initial value problem, and let's go back to the whiteboard. Okay. Oh my. So out of steam. Okay. I'm going to clear my drawings here. Here's example 5. Here's the differential equation. dy dx plus y is equal to x, with initial condition that y of 0 is equal to 4. Okay. I'll tell you folks, this is going to be a struggle all afternoon. 44 more minutes of it. I hope I make it. Okay. Now, good news, already in standard form. The coefficient already is 1. We didn't have to divide by anything, so we didn't introduce any singular values, singular points, so we don't have to worry about those. So we can jump right to our procedure. The P of X here, that's the coefficient of your Y here. Oh, here comes James. Perfect attendance again today. Way to go, folks. This class is so good at getting here. Okay, hold on just a moment while I mark James present. All right, perfect attendance, ding, ding, ding. My first class missing 1, second class missing 2. This today, perfect attendance. Way to go. All right. Was there a question? Okay. All right. Now, James, we're on example 5, chapter 2, first order differential equations, section 2.3, linear equations, example 5, near the top half of page 59. Okay? And it's an initial value problem. First thing we're going to do is identify our P of X. P of X is a coefficient of your Y. That's obviously just 1. So the next thing we do is integrate that P of X dx. And the antiderivative of 1 is just x. Now remember, when we do that integration, we don't put a constant in. We just go with the numeric part. Well, what do we do with that? We raise it to the e. So e to the x becomes our integrating factor, mu of x. Okay? And what do we do with that? We multiply that by everything on both sides of the equation. So this gives us e to the x dy dx plus e to the x y plus x xe to the x. I knew it was in there somewhere. Okay. Given that y of 0 is equal to 4, we'll come back and recall that later. All right. Oops, I knew something was wrong here. Y'all are letting me get away with it. Okay. That's an equal sign there, not a plus sign. Like I say, the old gray cells, they're just about asleep, passed out. It's hard struggling right now. All right, now supposedly the left-hand side, and let's confirm that it is, should be a perfect derivative of your integrating factor e to the x times your function y. Okay, let's see if that's the case. First times derivative of the second, sure enough, plus the second times derivative of the first, sure enough. And that's equal to x e to the x. Okay, what we're going to do now is write this in differential form. Okay, goodness, my throat is hurting so badly. I don't have any more sodas, so I'm going to have to drink water and see if I can make it feel better. And somehow, I think I said it, but either the pen didn't write or it erased itself or something, dx. Wrote that in differential form. Now, the antiderivative of a perfect derivative is itself, e to the x times y. And on this side, we take that derivative of that, and that's really what we did here too, to get that. And I think I'll erase that part. Okay, and let's go on and get working on what that derivative is. Anyone have a suggestion of what technique we use for that one? How about integration by parts? Let u equal x and dv, that's a v there, is equal to e to the x dx. You always have to have the d's together. This d here goes with that d there. Okay, wait a minute. I don't know why my eyes are drying out. I do have the ceiling fan on, but I've had it on for a while, so that shouldn't be the issue. But anyway, integration by parts, then du is equal to dx, which is fine, that's what we've got. And we're going to integrate both of these. V is equal to e to the x. Okay? Alright. Now we don't need to do a plus c there either. Okay? Because what we're going to do, we'll take care of that in a minute. Then we do uv. Okay? So this thing is equal to u times v. That's x e to the x. Okay, my drawer quit working. Excuse me another minute. I am so sorry. I think I've maybe had too much sugar and too much caffeine, because I'm getting a little wired feeling. Okay, this is equal to u times v. That's x e to the x minus the bottom line down here, which is the integral of the bottom line down here, which is e to the x dx. Okay, and we know what that is. So here's what we've got so far. E to the x times y is equal to x, x e to the x minus, and the antiderivative of e to the x is e to the x. Okay, and now we can put the plus c in there. Okay, now we're going to plug in our initial values. When x is equal to 0, y is equal to 4. Wait, let's see. Would it be advantageous to go on and divide? It may be. Let's do that first. Divide everything on both sides by e to the x. Yuck. Including the constant. Okay, now this will go away. This will go away. This is why I found it probably easier. That goes away to -1, and that stays. So what do we have? Y is equal to x minus 1 plus c over e to the x. Okay? Now, let's do our initial condition. When x equals 0, y is equal to 4. So that would be 4 is equal to 0 minus 1 plus c over okay, x equal to 0 e to the 0 is 1. So that's just plus c. So we don't need the line here. So add 1 to both sides, and what you get is c is equal to 5. So go back and plug that in here, and your solution would be y is equal to goodness gracious, x minus 1 plus 5. Something is wacko here. Plus 5 over e to the x. I knew something was missing. I was looking at the wrong line up here. Here it is. 5 over e to the x. Or, probably the better way of writing that is y is equal to x minus 1 plus 5 e to the minus x. That's probably a little bit better. Oh my goodness. It's a struggle. Okay, and that is the answer they got. Y is equal to x minus 1 plus 5 over 5 times e to the minus x. Perfect. All right, let's, for the moment, go back to the screen and pick up the verbiage there. Still got all 5 people here. Fantastic. I'm sorry. I just need to breathe a little bit. My head's clogged up. All right, here's example 5. Initial value problem here. The p of x equal 1, f of x equal x, are continuous on everywhere. Integrating factor is e to the x, which is e to the x, and when you multiply that by both sides, you find this exactly like we found, and that gives you, excuse me, I'm so sorry. E to the x is equal to, they didn't show the integration, but we did integration by parts here. X e to x minus e to x plus some constant c. Then you take that, plug in your initial value in. So this is your general solution with a c there, okay? And what they did here was divide everything by e to the x like we did. But from the initial condition, we know that y is equal to 4 when x equals 0. So when you put 4 in here, 0 here, that's a minus 1, and this becomes a plus c because e to the 0 is 1. Then you have c is equal to 5. And so the solution for the problem, everywhere in the interval, no singular solutions, nothing that you have to deal with there. So everywhere from negative infinity to positive infinity, x in that interval, y is equal to x minus 1 plus e to the minus x. Now, using a graphing utility like they have, they show the graph of that one this is the graph of this one. Now, of course, you have to have a graphing utility to draw that. But just showing when x's are very large, this thing goes to 0. So you're approaching y is equal to x minus 1. That's a line which has a y-intercept of minus 1 and a slope of 1. And that's exactly what you get here. for the long term. X very large up here and very small down here. Well, that's when C is equal to 0. Okay, that's what. All right. Uh-oh. I don't know what happened there. Let me see if I can move James out of the way here. I don't know why Word just decided to pop up there, but maybe I hit something that I didn't mean to. Okay, so when X is very large, this is going to the line here. And that line would be Y is equal to X minus 1. But when X is very small, then this thing can blow up because you're minus a minus number. That's a positive exponential. And when C is, okay, we found C is equal to 5. That was here. That's because when X equals 0, Y is equal to 5. I'm sorry, y of 0 is equal to 4. It's right here. Okay, and that's the one and only for there. For any other positive C's, you're up here, and your exponentials take over for small x's, and they take off and diverge this way. For C's less than 0, they're down here. When C's are above 0, you're up here, less than 0 down here, and they are diverging negatively always. Okay, now what I was saying about for very large x's, this becomes what they call a transient term that disappears over time. When x gets very large, this thing goes to 0, so that's a transient term. Okay, now in our original, there it was right here. So the overall solution, except for the fact that well, that's just the transient term when this thing is going to 0. Okay, okay. Now, what they call this is asymptotic behavior. As x gets larger and larger and larger, it approaches as a slant asymptote the line y is equal to x minus 1. Okay? It says, while that behavior is not characteristic of all general solutions of linear equations, and they say see example 2, the notion of a transient is often important in applied problems. So stand by for that. Now, next thing we're going to do is sort of a, whoops, well, going the wrong way. A piecewise linear differential equation. Now, this has some potential problems in it, but in the construction of mathematical models, especially if you're in the biosciences, engineering, it can happen that one or more of your coefficients in a differential equation is not just a simple function, but a piecewise defined function. In particular, okay, I'm having trouble breathing. Particular when either the p of x or the f of x in your standard differential equation, linear differential equation, is a piecewise defined function, the equation is then referred to as a piecewise differential equation. Okay, now I know that he started last time that when we're doing before, we always were dealing with continuous equations. Now, piecewise differential, if the p of x or f of x is piecewise defined, it doesn't necessarily mean you have a discontinuity of the function itself. You could have a discontinuity of the first derivative of the function, the f of x or the p of x. Okay, now the next example coming up, the f of x is a piecewise continuous function on the interval from 0 to positive infinity with a single jump discontinuity. So this is not a continuous, a jump discontinuity at x equal 1. So from 0 to 1 it's one thing, from 1 to infinity it's something else. The basic idea to solve the initial value problem in two parts corresponding to the two intervals over which f is defined. Okay, each part consists of a linear equation solvable by the methods of this section. Okay, as we'll see, it's then possible to piece the two solutions together, x equal 1, and that's what we'll show that will be happening. Okay, so, and they say refer you some future problems. So let's do example 6. Enough of the blah blah blah, let's actually do it. Okay, I've got the ceiling fan running and I'm getting really hot and I don't know why. Maybe exhaustion, I don't know. Okay, now let's go to our whiteboard. All right, example 5. No, example 6. Okay, so we've already done that one. So let's clear the screen. All right. Yeah. All right. Dy dx plus y is equal to f of x. Now, this is interesting. They don't tell you explicitly what f of x is. However, it's an initial value problem where y at 0 is equal to 0. Okay, that sounds like an initial value to me. But they also tell us where f of x is, and the f of x is 1 anytime that 0 is less than or equal to x is less than or equal to 1. It's 0 anytime x is greater than 1. Now, I wrote the greater sign, but not the 1. All right, there's our situation. Okay, now how are we going to go about solving that? Well, just start like we did before, but we're actually going to have two solutions here. Okay, and here's what we'll do. This is brute force here. Dy dx plus y is equal to 1. Now that's true anytime 0 is less than or equal to x is less than or equal to 1. And since our initial condition falls in that part, x equals 0, you're in here, let's solve that one with our initial condition. This one has nothing to do with the initial condition because x is greater than 1 here. So what we'll do is come back and try to match up things there. Okay, but let's worry with that first. Okay, this first. Standard form, coefficient here is 1. Coefficient here is 1. So your p of x is equal to 1. You integrate that p of x, and you get x plus, we don't do a plus c with it, it's just x, and then you raise the e to that power, and that becomes your integrating constant. We've seen this before, mu of x. So what do we do with that? We multiply everything on both sides by mu of x, and we have e to the x, and this is e to the x dy dx plus y e to the x is equal to 1 e to the x, because you're multiplying everything on both sides by e to the x. Sorry, my eyes are stinging so badly I can hardly keep them open. Let me see. Can I make it 17 more minutes, 18 more minutes? I'm going to try to. But let me at least, I'm sure rubbing's not going to do them much good. Man, they're so dry they hurt. Okay. So we multiplied both sides by the integrating factor. Now supposedly this left-hand side, if I can find my pen, here it is, should be d by dx of the integrating factor e to the x times y. That's what it should be. Let's check and see if that's true. Derivative of this would be, it's the first times derivative of the second. That's what you have. This is a product. So e to the x times dy dx plus the second y times derivative of the first, which is e to the x. That sure enough is true. The right hand side is simply e to the x. 1 times e to the x. Let's write that in differential form. Move our dx over here. If you integrate a perfect integral, a perfect derivative, you get e to the x times y is equal to, you integrate this side, and you get e to the x, okay, plus c. There you do need to do a constant, because this is an indefinite integral. This is the place you do your initial condition, put a y in for 0 and a y in for x, and this would be 0 on this side is equal to 1 plus c, because e to the 0 is 1. So c is equal to negative 1. So your solution here is e to the x y is equal to e to the x. I really don't like to do it this way. Minus 1. And let's multiply everything by e to the minus x to get rid of this. So you get y is equal to 1 minus, goodness, my nose is itching, e to the minus x. Okay. Now, that's a solution for this part of f of x. But we want it to be continuous there at 1. So let's see what the value is when x is equal to 1. When x equals 1, you have y is equal to 1 minus e to the minus 1. Okay? Now, I'm running out of room very rapidly. Okay, so this is basically almost another initial condition. It's not exactly, but it's y of 1 is equal to 1 minus e to the minus 1. Okay. Now, what we do is go back to our differential equation where it's equal to 0. Remember, we had two differential equations here. The second one, I don't have much room, dy dx plus y is now equal to 0, with sort of the kind of like an initial condition that y of 1 must be that. That's a condition of continuity. It's not an initial condition, but it's a condition of continuity. Okay? Well, if you go through the same thing, you get the same e to the x is your mu of x again. Everything works out the same, except when you get down to this line, you have e to the x dy dx plus y e to the x is equal to 0. Okay, because you got this f of x in there now. Okay, and that's one that is frankly, it's a separable equation, and let's go with it. I think e to the x dy is equal to minus x e to the x dx. You just subtract that from both sides, and basically you wind up with dy when you divide both sides by e to the x. That's not a minus x there. This is this one. Okay, hard to read. I'm having trouble following my own. Okay, we divided both sides by e to the x here, and you have dy is equal to minus x e dx. That's it, minus x dx. And we integrate both sides of the, well, wait, this y here. So I can't read my writing here. I think that's a y. Yeah, minus y. Oh, I know, I put x rather than y there. That's e to the x. Okay. So if you divide both sides by y, this is what you get. So this is log y, absolute value technically, but all your, we can't say that. Let's put in the absolute value just for safety, is equal to minus x plus c here. Now this c is not an arbitrary coefficient. This is one that we're going to basically connect by this. So let's put in these values. When x equal 1, y, okay, let's deal with this first. Y is equal to e to the minus x plus c. Okay, and when x is equal to 1, y is equal to that. So you get, I'm running out of room, this is getting all crossed up. 1 minus e to the minus 1 is equal to e to the minus 1. I'm going to rewrite this as ce to the minus 1 because it's a different c, but you get this. So divide both sides by e to the minus 1 and you get e to the 1, or just e minus 1 is equal to c. Okay, for continuity purposes you've got that, so this equation then becomes y is equal to e to the minus x plus, if I could read my writing there. Goodness gracious, I'm so sorry. I've got to get rid of that thing. Okay. Go away. Okay. Let's just go back to the book because I don't have enough room to write here. We'll just pick up where I left off in the book. Okay. Hopefully, goodness gracious, I'm so sorry. All right. Let's see. The graph is a discontinuous function here. F of x is 1 from 0 to 1 and then 0 everywhere else. Okay, that's your f. We solve that differential first on the interval 0 to 1 and then on 1 to infinity. For 0 to 1 we have this, or equivalently this is exactly what we had. Okay, integrating that last equation gives you y is equal to 1 plus c1 e to the minus x, and since y of 0 is 0, in other words, x is equal to 0, y is equal to 0, that makes c1 equal minus 1. Yeah, we got that. Therefore, y is equal to 1 minus e to the minus x. My clip has come off. This is such an aggravating thing here. Okay. All right. So solve this for when c1 is minus 1, that's what we were doing. You get y is equal to 1 minus e to the minus x. And that's what we got. And that's good for everywhere the x is between 0 and 1. When it's greater than 1, then this equation holds. Okay? And that leads to this, and I think that's pretty much what we got. Okay? Now, you get this form for anything x between 0 and 1. This form anywhere x is greater than 1. Now, that's what I was saying. You appeal to, and we lost somebody. No, yeah, we lost a couple people, it looks like. Appeal to continuity at the point. It is possible to determine C2 so that the foregoing equation is continuous x equal 1. The requirement is the limit as x approaches 1 from the right must equal y of 1 from the left. And that implies that c2 e to the minus 1, and this is what I think we had written there, is 1 minus e to the minus 1. So if you multiply both sides by e, this becomes c2 is equal to e minus 1. And that's exactly what I think I had written down there. And then you can put this in. Y is equal to 1 minus e to the minus x anywhere you're there. That's from this one. And then this one would be y is equal to e minus 1 times e to the minus x anytime x is greater than 1. That then becomes something that's continuous on the whole interval. Its derivative isn't continuous, obviously, but the function is continuous. But you see, from the very top, the derivative wasn't continuous, because the derivative up here, where is it? If you added or subtracted y from both sides, the derivative would be 1 minus y up here and 0 minus y here, or minus y here, and that's not necessarily continuous. In fact, it isn't continuous. And sure enough, we see that. But you do get a continuous function then. So the second, this is what I was trying to say, the second constant here is not an arbitrary constant, but what I called a continuity constant. Okay, and that's just made it match up right there at that point. The first one, there was your initial value, so you're right here. The second one is a continuity constant, so you continue there. Now, here they introduce something new. We only got 3 minutes, so let's see if we can get this done. In mathematics, science, and engineering, some important functions are defined in terms of non-elementary integrals. Haven't we seen this before? Two of these special functions are called the error function and the complementary error function. The error function is this weird thing, 2 over root pi, which pi itself is an irrational number. Root pi is going to be a more irrational number if you could get that, times the integral of 0 to x e to the minus t squared dt. Remember, that is not an integral we can integrate. Okay, now the complementary error function to that looks just like it, except now this is going from x to positive infinity. Okay, and the rest of it is exactly the same, and we still can't take the integral of that thing. Okay, so from the known result that from 0 to infinity, that's combining those, this thing is equal to square root of pi over 2. Okay, now it says the result is proved in example A. Okay, so if you want to go back and eat this one up, you can. Okay, so with that in mind, then that 2 over root pi integral from this is equal to 1. Okay, now they say this and say we can write this. Okay, but you see what we mean there is to add this to that. Okay, and that's what they're doing here. They're leaving off the integrand, but those are exactly the same in both cases. We can recall that the last result in the alternative form, that's the error function plus the complementary error function, and they have to equal 1. Okay, same from 12, that the error function ERF of x and the complementary error function ERFC of x are related by this identity, that the sum of those two is always equal to 1. Because of its importance in probability, statistics, and applied partial differential equations, the error function has been extensively tabulated, and the error function of 0 is 0, and then you can calculate it from there on. Okay, and they also have tables of them. Or you can use a computer algebra system like Mathematica or Maple or one of those and get it as well. Now, I don't know that they give us, do they give us an example with this one? I'm thinking, yes, they do. If we are solving the initial value problem and we are out of time, we're going to start here at the top of page, where are we? Yeah, top of page 61. And that's pretty much where we ended last time I taught this. I'm just going to move us to the top of the page. Okay. And let's see if we can find some homework exercises here. We almost finished this. We'll wrap it up next time and move on to 2.4. Homework exercises, any of the odds 1 through 23 that are in the back of the book, try to do those. Now some of these may be some that we haven't done yet. If they are, skip them. Okay? No, we should have done all these. So yeah, you should be able to do all those. Any of the odds 1 through 23. Any of the odds 25 through 35, you should be able to do those. And then the next one, based on example 6, you should be able to do 37 or 39 and 41. Okay, hold off on 43 and following. We'll pick up those next time. All right, any questions? Sorry it's been such a difficult day, but man, it's just about over. So got a lot of work to do before I crash, but boy, when I crash, it's going to be hard, I think. Any questions? Okay, I'm going to stop the sharing, and if there's no questions, I'm going to end the recording there. So good deal, folks. Glad you made it through, slug through with me. We'll end the meeting. We'll see all 3 of you tomorrow, okay? And then we'll see you again on Wednesday twice. All right, take care, folks. Bye-bye.